on the handy dandy little scale. Now, I have this written down right down here. Alrighty, so we found out that it was basically 30 grams, I believe. It was right around that. It's really hard to see, but I think it's around 30 grams. Alright, we're going to take that into kilograms because the unit of measurement for mass is in kilograms. Kilograms is the mass. Let's see. So there are 1,000 grams per 1 kilogram. So what you would do is you would take the 30 grams. Let's see, we're going to get rid of this. 30 grams divided by our, what do we got here? 1,000 grams. There are 30 grams divided by our 1,000 to figure out how many, what 30 grams is in kilograms. What would that be? Oh boy, it is 0.03 kilograms. Not very much. But I guess it's a very small car. There we go. P equals 0.3. We're going to multiply that by our velocity value. And our velocity value is 0.3 as well. Times that by 0.3. We're going to have, if I'm not mistaken, I'm believing it's going to be 0.9, but let's check. Let's check and make sure first. Because I would hate to be wrong. Let's see. 0.9. 0.9. No. What the heck am I doing? Here we go. 0.3. Getting carried away here. 0.3 times 0.3. Dang. Today is just not my day. 0.3 divided by times 0.3. See? There we go. No, it's 0.09. Oh, see, I'm glad I checked that on the calculator. 0.09. Alrighty, and that is in, that would be momentum, and that is measured in, and it is measured in kg times impress. So let's put this down here. I'm trying to get this camera to clear up. There we go. Kg, well, couldn't really use the traditional times because that's turned into X nowadays. Let's see. Give me a moment. Okay. Kg, we're going to have times m per s. Here we go. See, kg times m per s. That would be our momentum value is 0.09 kg m per s. Alrighty, so now it is time to find the kinetic energy. Fun stuff. Let's see. Our kinetic energy. You would take 1/2 multiplied by mv squared, the mass times the velocity squared. So we're going to take our mass, and our mass, when we found out what this was, it would be 0.3. So we're going to take our 0.3 value. Let me see. So we got our 0.3 value up here. And we are going to now multiply that by, let's see, multiply it by, what was our velocity value? It was 0.3. And we're going to square that because that is what it says to do right here on this formula. 0.3 times 3 squared. Find that. Alrighty, now what we're going to do now is just divide it by 2 because just multiply it by 1/2 is the same as dividing it by 2. 0.0135. Okay, so our kinetic energy would equal KE is equal to 0.0135. Man, I need to work on handwriting. And it is measured in, I believe, joules, because joules are, let's see, it is kg multiplied by m squared divided by s squared, and that is the same as a joule. So we have 0.0135 joules. That is the kinetic energy value. And this car is demonstrating Newton's 3 laws, because when the force acts upon it, it moves. and the force acts upon it, and I stop it, it stops. So the thing is, it keeps moving unless there is an external force acting upon it. Now, if I was just to leave it going, it would eventually slow to a stop because of the force of friction acting upon it. This floor is a little bumpy, so it's very, very much a friction surface. A lot of friction in the surface, and it is also things when you exert. See, it doesn't have much mass, but when you exert a lot of force on it, the acceleration is going to compensate for that lack of mass. Because if there is a large acceleration value multiplied by this small mass value, it's going to equal the amount of force that you've used to push it, and that is Newton's second law: F equals ma. Force is the mass times the acceleration. If there's a small mass, there's going to be a larger acceleration to compensate for that force, to explain this force. And the third law is the law that states that it would state that that the velocity. See, the thing is, it would state that. See, if I could get this thing moving fast enough, if I could get this cart to move fast enough, it would. If I put my hand down to stop it, and it ran into my hand, it would bounce backwards because of the force upon hitting this wall that is my hand. It would bounce backwards. Let me see if I can get it to do that. Let's see. Doesn't want to do it. I could feel it bounce back off my hand a little bit. I'm not sure if I can get this very. There we go. It bounced just a little, just then. Just a very little. There we go. It bounced just a little bit, but it did bounce. And if it was going even faster than that, it would likely bounce more off of my hand. And that is Newton's third law. Now, I will show you the schematic for this little car that I drew. It is called the Lego Mobile. It's kind of the Batmobile, just not quite as well designed and with all the knickknacks and doodads. But right here I have the diagram. It says it has, this is the bottom of the car. I didn't get the top, but I figured the bottom would show more the whole thing with the wheels and axles. I thought it'd show that better. But matches pretty well, I thought. But so the axles, we have lines going to this little area right here between the wheel and this part, which would be on the car, it'd be here and this part. And it goes from, on each wheel it shows that. See, lines going there. Now, for the wheels it shows, I have lines going to the wheels. Down here I have another, there we go, Lego bricks that indicate this right in here and this right in here. Those are Lego bricks. And I have a little sketch of the side of the car. Here we go. And that is my toy car.